All right, so now we will continue where we left off from the previous lecture. Last time in the previous lecture, we saw some basic commands for setting up a reactor, which will almost certainly be used in all of the scripts that you write. Today, we will see those commands in action and also look at some of the attributes of the reactors in Cantera. So let's get started. All right, so as always, we will execute the lines one by one in the console so that we can see step by step how each command behaves. But let's start with defining or rather importing Cantera first. So import Cantera SCT, right? Gas equals CT dot solution. This time, let's use the hydrogen oxidation reaction mechanism, or the hydrogen oxidation input data file. That will be H2 O2 dot YML. Okay, so we can also take a look exactly what does it have right now. Again, it has initialized hydrogen as one. And if you want to see what all species are involved, we can just write gas dot species, right? So in hydrogen peroxide, or rather hydrogen oxidation input data file, we have all of these, I believe, 9 species. So hydrogen atom, O, O2, OH, etc. So we have these 9 species in H2O2.YAML. Okay, so now let's go ahead and define the thermodynamic state of this phase. So that will be gas.tpx equals 1000, comma, CT.1 atmosphere, comma, H2, say 0.2, and anything else, like say O2 can be 0.3 or something. The Cantera will anyways normalize this composition. Okay, now let's go ahead and initialize a reactor. So we will say R1 equals CT dot ideal, is that right? Yeah, ideal gas reactor. And we will initialize this ideal gas reactor with the gas phase. We do that. Okay, now, if you want to look at the thermodynamic state of the reactor at any given point, what we have to do is to use, there are multiple ways. One is you can say R1 dot thermo, and this is what you'll get, which is it'll show you what the initial phase or what is the current thermodynamic state of the reactor. In this case, we've initialized it with 1000 Kelvin, 1 atmospheric pressure, and the density is calculated on its own, depending on the composition that we provided. So we provided TPX, right? So that's the temperature, pressure, and X would be these mole fractions. And you can see Cantera has normalized. So we provided 0.3 and 0.2 and 0.3 to make the whole thing as 1. Cantera changed these mole fractions to 0.4 and 0.6 for hydrogen and oxygen. So this is what R1.thermo does. There's one more way of looking at things, that is R1.getState. This is another function from which is for these reactors, for the idea for any reactor as such. So if you look at the gas state, this is what it gives. Now this looks a bit strange, but if we look at the help for get state, we will come to know what this does. So help R1 dot get state. Okay, so this shows you here, if we have ideal gas reactor, then the first, or rather the 0th element of the entire array output array will be the mass, which will be this number here. Then the second one, or the first index, would be volume. Then it will be temperature, which is 1000, what we specified. And then it will be the mass fraction of the species. So these are all the 9 species that we have. This is hydrogen. And this follows the same exact sequence. So if you look here, or rather we can, okay, so you have hydrogen, and oxygen is the 4th species. So hydrogen is first, oxygen is 4th. Here we have hydrogen and oxygen. This is the first species, because the species start from 3 plus. So this is 0, 1, 2, 3. That's hydrogen, and this is oxygen. That's the mass fractions. So you can use get state as well to, and if by chance you have a constant pressure reactor or ideal gas constant pressure reactor, then there's a slight difference. Instead of volume and internal energy, you just have enthalpy or temperature. That is because the state variable for these two reactors, instead of temperature, it is enthalpy. So all the equations are solved in enthalpy, and then temperature is sort of back calculated. So that's for some of these functions for reactors. Now, that one more thing that we can also try is you can just simply look at some, say, for example, the temperature. So R1 dot T, that gives you 1000 Kelvin. Now, if we want to, so this reactor right now has been initialized with hydrogen and oxygen in 40:60% ratio. If we want to solve this system, or rather look at the progress of reactions in the system, we will have to step it in time. And as you remember, if you remember from the previous lecture, we will have to use a special class, which is the reactor net class. And so what we do is we say R1 is equal to, or not, sorry, let's call it sim equals CT dot reactor net, and then the name of the reactor. In this case, this is R1. Right? Now, using this line, sort of a network has been formed where R1 is a part of this network, and now you can solve this network to see how do the reactions progress in this particular reactor. So all we have to do, there are two ways actually. Let's go with the simpler way first, and then with the more advanced way. So that is, we can say R1, or rather sim dot step. Now it has spelled out a number. This is what it does is, when you say the name of the network, which is sim, that you can see from here, the name of the network dot step, the whole reactor steps in time, and it takes the smallest step so that it can calculate the next state of the reactant. And so it has taken a time step of 9.12 into 10 to the power minus 13 seconds. Now, if you say sim dot step again, it will always, whenever you say dot step, it will spit out a time. So if I say sim dot step, see, now this number has changed. And so now this time it has taken a time step of 2.7 10 to the power minus 9. So this is an internally calculated time step that Cantera uses. And you can also look at the temperature, for example. So R1 dot T. Now see, as the reactor is progressing in time, the internal state of reactor is also changing. And we can again take a look. So from 1000 Kelvin, it has dropped down by a very small fraction because it has taken very small time steps. And so we can say get state, And now you will see everything has changed by a very small number. All the mass fractions have changed by a very small number. So this is how a reactor steps in time. There's another way, which instead of taking these smaller steps, that method takes you straight to the intended timestamp. So there, what we say is, say, for example, if I say T, or I can just say sim dot advance 0.01, for example. Now what it has done is, instead of taking one small time step of this 2.7 10 power minus 9 seconds, for example, Cantera has internally taken many time steps, multiple time steps, and integrated the entire system to 0.01 seconds. And now, if we look at the state, so you say, sorry, R1 dot get state. So you see, now everything is extremely different. And if we just look at temperature, now see, so from 1000, the temperature has gone up all the way to 3082 Kelvin, because hydrogen and oxygen are reacting. And this is the temperature at 0.01 seconds. So this is how you step in time or integrate the reactor system in time to find out how the thermodynamic state of the ingredients of the reactor are changing. So that was it for this lecture. In the next lecture, we will see how to exactly use these functions and the time advancement as well in an actual problem using a script. All right. Thank you so much.